I want us all to realize that counting is actually a bijective function. How so? When we try to count objects, we're associating numbers, natural numbers starting from 1, 2, 3, and then onwards as far as you can count every positive whole number that you can think of. We are associating a sum or some or perhaps all of these numbers, as we will see later on. Well, but for now, some of these numbers with items that we see. So let's say I have a list of items that I want to count and a list of numbers I'll use to count them. So I look at this chair in a room, right? So I see a chair in a room and I say, okay, this is the first item I'm going to count. So I associate 1 with the chair. I look at this table and I think, well, I'm going to associate 2 with this table. And there, I counted it as 2. I look at this lamp and I think, well, lamp's going to be 3. Then I look at this cup of tea, and I think that, well, you're going to be the 4th item I'm going to count. And I look at this cube, and I think, well, you're going to be the 5th item I'm going to count. Now notice something interesting about bijective functions. So if a function is bijective, we notice that in essence, it's like each arrow that you see here, right? Each arrow that you see here will relate a pair containing one element from the first set and one element from the second set. And in this manner, each arrow produces multiple pairs, and these pairs have the property that, well, none of their elements match. I'll show you a better example. So let's consider this set over here. These two sets. Let's say the first set has the elements A, B, and C, and let's say the second set has the elements X, Y, and Z. So this function here is a bijective function. If so, the pairs that we produce look something like this. So we have A and X being related, B and Y being related, and C and Z being related. And notice the pairs that were formed from this bijective function are such that if I had to compare any two pairs, like let's say I compare the first and the second pair that we see here, I see that their first elements are different and their second elements are also different. Take any two pairs, try to compare them, and you will see that none of the first elements will match, none of the second elements will match. So that's the thing. So basically, I can always represent a bijective function using arrows in this way, as in an arrow joining one element from the first set to an arrow joining one element to the second set in this manner, such that I don't have, let's say, multiple arrows starting from the same first set element. Like I can't do this, that's not allowed. And furthermore, each element in the second set has at least one arrow attached to them. And furthermore, if two elements are different, they are related to different elements. So we have all of that going on here. So you can look at it as a bunch of parallel arrows, perhaps, and perhaps not even, it's not necessary that they have to be parallel arrows for that matter. I could have something like this, right? So A, B, C, X, Y, Z. I could do a crisscross, something like this. And it would still be a bijective function because now the pairs are AZ, BY, CX. And once again, the first elements of all of these pairs won't match, and neither will the second element of any of these pairs match, right? So when we have this concept out of the way, we realize that counting behaves in the same way. I now have a pair, 1 and a chair, 2 and a table, 3 and a lamp, 4 and a cup of tea, 5 and a box. And we see that none of the pairs have their first element to be the same, nor are their second elements the same. So yeah, counting is actually a bijective function. And to see this more explicitly, counting will, of course, satisfy surjectivity. because each element in the second set, given that we have counted successfully, it means I must have counted the table, right? Like, consider any element from the second set. If I have successfully counted, this element in the second set must be related to someone in the first set. Surjectivity guarantees that. And furthermore, injectivity guarantees that if two numbers are different, then I must have used them to count different things. I won't use the same number to count the same thing. That's guaranteed by injectivity. So we understand that counting truly is a bijective function. It satisfies both the necessary properties. And furthermore, interestingly, if I had a bijection, right, a bijective function, if I had a bijective function between two sets, a first set and a second set, it is as if these two sets are precisely equal. Well, why is that? Because bijective function, in the same manner that counting behaves like a bijective function, any bijective function behaves in the same way as counting. Because, as I have just explained, injectivity prevents double counting, in the sense that if two elements are different, I use them to count different things. So I'm not counting twice. And surjectivity guarantees that each element of the second set is associated with someone from the first set. So in essence, I've counted everyone, that's for sure. Surjectivity tells me that I've counted everyone. Injectivity tells me that not only have I counted everyone, I have counted everyone once. Once using each element from the first set. So that means each element in the first set was used to count someone in the second set. This can only mean that these two sets have the same number of elements. So having a bijection is the same as, let's say, having the same number of elements. It's the same as counting. So what this means is I don't always need to painstakingly count large sets. And we will use this idea to compare sets that are infinite. If two sets are infinite, there really isn't a size that I can use to compare them. So instead, we'll compare them using bijections. Using bijections, perhaps I could say that two sets are equal, or maybe one set is bijective to a subset of the second set, in which case it is a smaller set then clearly. So we can use concepts like these.